Just like a summary slide of what we looked at last week. So we defined some terms, if you remember, terms like distance and displacement, velocity and speed, and so on. And we're looking at these equations of motion. They're on the right hand side here. Actually 5 equations of motion, sometimes called Newton's equations of motion, actually, linear motion. So I've some 5 here, and you get those 5 in your formula sheet in a slightly different order, but they're in your formula sheet. And they all relate to constant acceleration. That is quite a key underpinning assumption here. If you had varying acceleration, they actually don't work. But in a lot of situations, you can assume constant acceleration. So they're quite valid equations. I've used them in industry. And they all really derive effectively from the velocity time diagram on the left-hand side here. That velocity versus time diagram, a very useful diagram. Velocity on the vertical axis in meters per second, time on the horizontal axis in seconds, of course. The slope of that line, the gradient of that line, relates to acceleration. And the area under the graph, we're actually calling it distance travelled. It actually is displacement, to be correct about this. We talked about the difference between displacement and distance last week, and the area under a velocity time graph is actually displacement, but for the questions that we are going to look at, distance and displacement are one and the same thing. If we're just looking at straight line linear motion of, say, a train being accelerated to a maximum velocity, holding that maximum velocity, and then decelerating to rest. And so the distance travelled there is the displacement. So just be aware of that. If you look at other textbooks or a good high-level study, they may talk about displacement, and it can be a different quantity to distance. It depends on the scenario that you're considering. But in our case, the area under the velocity time diagram is basically distance travelled. So that's quite an important characteristic. So gradient of the line is the acceleration. Area under the graph between 2 points we're considering is the distance travelled. So the right-hand side is all the equations that we derive basically from the gradient of the line and the area under the graph there. Okay. Now last week we looked at example 1. But example 1, we were considering a cyclist. It was accelerating from rest, if you remember now, to some maximum velocity. It held that maximum velocity for a period of time and then decelerated. That's a negative acceleration, and to rest again. I'm not going to go back through that now because you've got that in your notes, or you can look at the previous lecture online. So exercise 1, in this case we have a diesel train, and it accelerates uniformly, constant acceleration there, from rest, that's 0, to a speed of 70 kilometers an hour. Be careful of that, for a period of 30 seconds. We're told it continues at this speed for 60 seconds, and then it decelerates uniformly to rest, back to 0, in 60 seconds. We've got to calculate the total distance travelled in this particular case. We've got to calculate the acceleration and the deceleration of the train. So the first thing to do is to try and extract the information from the question and draw a velocity time diagram. This is my diagram for the exercise 1. So as you see from the graph I've got my velocity on the vertical axis as always, and my time taken on the horizontal axis. Okay, and I'm drawing my diagram here. If I can sketch a line here. The A to B would be the acceleration phase. I mean, accelerating from 0 velocity to some maximum velocity, 70 kilometers an hour in this case, holding that velocity for a period of 60 seconds, and then I'm decelerating down to 0 again. So that's what you should see. Now what you'll be careful with these questions is that although that diagram, that velocity time diagram, looks very similar to last week, it could actually have different information given. So the same velocity time diagram can actually ask you to find different parameters and give you different information. If you look at the previous example 1, we didn't have the maximum velocity, but we did have the acceleration given to us. In this case, we have the maximum velocity, but we don't have the acceleration. So you can see you can play tunes on these questions, even though the velocity time diagrams look the same. Be very careful because they can actually be asking for different information. In exercise 4, when you get there, that will have probably a very similar diagram to this, but the information given is totally different. So be careful when you get to exercise 4. So let me take you through this then very briefly. I'm going to let you try and engage with this. Hopefully you can have a go at some of these questions on your own. I'm just going to try and support you here with what we're doing. So taking information out of the question, one of the first things I noticed in this particular question is the velocity was given as 70 kilometers per hour. So we always use meters per second. So the first thing I want to do is to convert my velocity. Hopefully you remember the conversion. We multiply the 70 kilometers per hour by 1,000. That's converting the kilometers to meters, and then divide by 3,600, and that converts the hours to seconds. So that's my conversion. I get a value there of 19.4 recurring for meters per second. All right, and that's actually what I'm showing on my diagram. How it's shown on my diagram, 19.4 meters per second is 70 kilometers an hour. So just looking at what it's asking us to do, it says calculate the total distance travelled in this particular case. So let's see what we can do in working out the distance travelled. Don't forget the distance travelled is the area under the graph, area under the velocity time diagram. So we'll have the area of a triangle, we'll have the area of a rectangle, and then we'll have the area of another triangle at the end there. And this is very similar to last week's work. Look at example 1, it's very similar. We have the base of the first triangle, and we have the height of the first triangle, so that's fine. We have the base of the rectangle, the height of the rectangle, we have the base and the height of the final triangle. So can I let you work out what the distance travelled is, in other words the area under the graph, for that particular velocity time diagram? I'm going to leave you with that for a few minutes. If you're unsure, go back to what we did last week in the calculations for example 1. The answer, it says on the sheet, is 2.04 kilometres. That's 2,040 metres, probably in your calculation. So for my acceleration phase, which is A to B as I've labelled it, I've got 291 metres. For my constant velocity phase, I labelled B to C. I get 1,164 metres. And then for my deceleration phase, I've labelled C to D. I've got 584 metres. So hopefully getting something similar. So total that up, get 2,039 actually here metres. Probably a little bit of rounding there. So somebody getting 2,040. That's fine. 2,040 is fine. Okay. Next thing it wants us to find the acceleration, so that will be the slope of the line AB. So the acceleration is this gradient of the line A to B, and it also wants us to find the deceleration, so obviously that's the gradient of the line C to D. Okay, so again, I'd like you to have a go at that. You're given in the question the maximum velocities. You know the initial velocity. For our notation we use the U is initial velocity and V is final velocity. So for our acceleration phase A to B, U will be 0 and the final velocity V will be 19.4 recurring meters per second. But for the deceleration phase, don't forget to get your U and your V in the correct orientation. U is always the initial velocity of a particular phase of a diagram, and V is always the final velocity. So U occurs at C and V occurs at D on the deceleration phase. So again, can I let you have a go at those two questions? First of all, find the acceleration, A to B, then find the deceleration, C to D. Okay, so find the acceleration. I've labelled A with the suffix AB to show it's for the distance from A to B on my diagram. So what you've got to think of here, given information in the question, what equation is going to be useful to us? So we're given the maximum velocity V, we know the initial velocity because it's starting from rest, and we know the time taken. So what you need to do is go back to your equations, back to these equations here, and try and pick an equation that will link the initial velocity with the final velocity, with the time, with the acceleration, and then use the appropriate equation. Sometimes you'll need to transpose them, sometimes they'll be in the correct format for you. This particular question, I think we can use equation 1. To me, it looks the right one to use. We've got the initial velocity, we've got the final velocity, we've got the time taken. So a little bit of rearrangement, we can find the acceleration. Put down the equation first of all. So I'm going to put from my V equals to U plus my AT. And we've got to transpose it to find the acceleration in this particular case. So my transposition will be A is equal to V minus U divided by the time taken. I've got all this information in the question. So v in this case was 19.4 meters per second minus u was 0 in this case, and that's all divided by the time taken, which was 30 seconds. So again, make sure you put the values into the equations, and I get a value here of 0.648. The units, of course, don't forget for acceleration, meters per second squared. Perhaps I can let you now have a go at the deceleration, which will be from C to D in your diagram. So find the deceleration. I think in this case it's fairly clear to see it's the same formula again. It's just different information we've got given to us. It will be 0 minus the 19.4 recurring divided by the time taken. In this case it was 60 seconds. So that gives you a negative value for acceleration, which is what you should get. So I get negative 0.323. Again, units, meters per second squared. Do go through the calculations yourself to make sure you no problem with your calculator here working out these values. Show the full solution there. So exercise 1, very similar diagram to example 1, but slightly different calculations involved because of the information given. Okay, exercise 2, what I would like you to do is to extract the information from the question here and try and draw the velocity time diagram first of all. So read the question carefully. There is my velocity time diagram. You'll sketch yours like mine, the information given. So the car accelerates uniformly from rest, so it's going from rest again. And we're given the acceleration this time. We know the slope of the line. Don't forget, acceleration is the slope or the gradient of the velocity time diagram. So we know that slope there. So it starts from rest. That occurs in 11 seconds. So on the horizontal axis, we've got 11 seconds for the time of the acceleration phase. And then we're told that the vehicle continues at that maximum speed. We're not sure for how long, but it continues at maximum velocity from there on. So that's my diagram. So no deceleration phase in this particular question. So extract the information we know from the question. We know the acceleration, it's 0.6 meters per second squared. We know the initial velocity u, so over here, will be 0. And we know that the time taken for the acceleration phase is 11 seconds. So the first thing I can see we're clearly missing here is the velocity. What is the maximum velocity of our graph? We're going to need to know that if we're going to work out the areas under the shapes here under the line. Defined maximum velocity. And I think I'll use the equation given to us in our notes of v is equal to u plus at. So I get 6.6 meters per second. So I can find the area under the acceleration phase, A to B. And I've got to find how long it takes to travel the 75 meters, I think in this case it's looking for. So I need to know how far along it's gone into the constant velocity phase. But what I'm going to do is work out the area under the triangle for the acceleration phase, subtract that from 75, and then I'll know my area under the constant velocity phase, which is a rectangle. And because I know the height of the rectangle, the area, I'll be able to work out from the base of the rectangle, which will be the time. So it's very much like example 1 in our previous lecture, part D, I think that was. So let's see what we can do to work out the area under the section A to B of our diagram. So I'm going to find a distance travelled from A to B. Alright, so that's my acceleration phase, in other words, on my diagram. So S, I'll call it A to B again, because that's the phase of the diagram I'm considering. And that will be my base times height divided by 2. So the base, 11 seconds, multiplied by the height, which is the velocity, which is calculated 6.6, and that's all divided by 2. I get a value of 36.3 meters. Don't forget that distance travelled is the area, so 36.3 meters in that first phase of the diagram. Now, if I subtract the 36.3 meters from 75 meters, because that's total shaded area there, I'm effectively saying it's 75 meters, I can find the area I've got in my constant velocity phase from B to C, and then I'll be able to find out the time taken to travel that distance. 3. Find distance travelled from B to C this time. So basically that's going to be 75 meters subtract the 36.3. So the S from B to C will be equal to, if you want some symbols, some of you like symbols, it would actually be S from A to C minus the S from A to B. If you want symbols, don't worry. If you don't want the symbols, just ignore them. Just write down 75 meters. That's the distance from A to C, and then minus the 36.3 meters, which is the distance from A to B. It works out to give us 38.7 meters. So that's the area on a velocity time diagram between B and C. I'm just going to sketch the diagram again. I'm trying to find in this case the time taken. So the time taken for 38.7 meters will be across here. So time, again, if you want some little symbols, it's time from B to C is across here. So it's really just the area of a rectangle that we know. We know a height of a rectangle, and we've got to find the base of the rectangle. So to find the time taken, it will simply be the area, and I'm going to use symbols here, that would be the distance, B to C, divided by the height in this case, which would be the velocity, V in this case. If you want symbols, that's what the symbols would show you. Then that will be my 38.7 divided by the velocity, which was 6.6. Engineers use lots of symbols when they're defining and doing equations. Some students I know do engage a bit with the symbols. So that value, according to my calculations, t from B to C in that constant velocity phase, I get 5.86 seconds. That's not the answer to the question, don't forget. He wants to know the total time taken, so we need to find that finally. So total time taken, again a symbol that would be t from A to C in my diagram. So t from A to C, just add in my values up here. You know, that's 11 seconds to this point here, and we just worked out it's going to be the 5.86 seconds. So there's, adding those up together, we'll get 11 plus my 5.86, so 16.86 seconds. That's our final answer in this case. Okay, so again, I hope that was all right. Let's go back to the full question now. Exercise 2, and our full solution. Worked out the maximum velocity first of all, worked out the distance travelled from A to B in the acceleration phase. Then we calculated the distance travelled in the phase B to C, and then we calculated the total time taken, which is what the question wanted. So that's our final answer here. Exercise 3. A body accelerates at 0.2 meters per second squared for 15 seconds, then travels at this speed for 2 minutes. The body then decelerates at 1.8 meters per second squared to rest. We're asked to draw the velocity time diagram and then determine 1. the speed of the body after 15 seconds, 2. the time taken for the deceleration, and 3. the total distance travelled. I'm going to let you attempt this question on your own. The answers are shown here in the brackets. I would make the assumption here that the body starts from rest. It doesn't actually say that the body starts from rest, but I would make that assumption here. I'd encourage you to attempt this question. I will put the full work solution to exercise 3 on the next slide. Here's exercise 3, the start of the solution. On this slide I've extracted all the information given in the question. So we're told the acceleration is 0.2 meters per second for 15 seconds. So extract the information over here. That relates to this part of the diagram. And we're told that the body travels at the maximum speed for 2 minutes. So I've converted that into 120 seconds shown here. And we're also given the deceleration is 1.8 meters per second squared. And again, I've extracted that from the question, but notice I put the negative 1.8 meter per second squared because the deceleration is a negative gradient on our diagram. So that's the gradient from C to D here. And here's exercise 3, the full solution. So the first thing I've calculated here is the maximum velocity. Next, I've calculated the time taken for the deceleration. And finally, I've calculated the total distance travelled, which is the total area under the graph. Exercise 4 relates to what's termed a planing machine diagrammatic sketch shown here, and that's where a tool gouges out material from a component. So the context of this question relates to the movement of the tool on the planing machine. So a planing machine accelerates from rest to a maximum speed of 80 millimeters per second. We need to be careful with that information. And that travels over a distance of 8 centimeters. Again, we need to be careful with these units. The planing machine continues at this speed for a distance of 48 centimeters. It then comes to rest in 8 centimeters. Assuming that the acceleration and the retardation to be constant, we've got to calculate the total time taken for the stroke on the planing machine. We're given a hint for the conversions between centimeters and meters in the question. Again, I'd like you to attempt this question. Answer is shown on the right hand side, 10 seconds. What you'll find here is when you sketch the velocity time diagram, it will look very similar to previous velocity time diagrams we've sketched, but actually the information given to you is totally different. So you need to be very careful which formula you need to calculate the appropriate values and given the information in exercise 4. Also be very careful with your conversions. Make sure your speeds are in meters per second and your distances are in meters. Again, I would encourage you to attempt this question, but I will put the full work solution on the following slide. Here's exercise 4, full solution. So extracted the information from the question and I've drawn my velocity time diagram. Notice it does look very similar to previous velocity time diagrams with our acceleration phase commencing from 0 velocity to some maximum velocity. And we've got a constant velocity phase, and then we've got a retardation or a deceleration phase. Notice also that I've converted the maximum velocity in terms of meters per second, and also the areas under the graph I've converted to meters. Very important that we do that. And notice also from the question that the distance travelled in the acceleration phase is the same as the distance travelled in the retardation phase. That's 0.08 meters. Distance travelled in the constant velocity phase is 0.48 meters. So the first part of the question, I found the time taken from A to B. That's in the acceleration phase. Notice this time with information given, I'm using a different equation. In the previous questions, we often use V is equal to, and in those questions, we're trying to find distance travelled. But in this particular question, I am given distances. So therefore, I need an equation from our table that will allow me to relate distance to velocities into time. And this is the equation I'm using. S is equal to V plus U in a bracket multiplied by T. That's divided by 2. I've had to transpose the equation to make T the subject, so the time taken to travel between A and B. And the formula was 2 multiplied by the distance travelled between A and B, all divided by the velocity of V plus U. Inserting my values, I find it's 2 seconds for the acceleration phase, and because of the information stated in the question, that means it will be 2 seconds also for the deceleration phase, C to D. In part 2, I have to find the time taken, this time from B to C, the constant velocity phase, and again I'm using the same equation as shown in part 1. This time I'm finding the time between B and C, so that's 2 multiplied by the distance travelled between B and C over the velocities V plus U. As this constant velocity phase here, the velocities V plus U will be the same. My distance travelled is 0.48 meters. So evaluating from the formula, I get 6 seconds for the constant velocity phase. So step 3, to find the total time taken, that's from A to D on my diagram above. I just simply add the 3 times together for the acceleration phase, the constant velocity phase, and the deceleration phase. So the total time taken by the stroke of the planing machine in this case is 10 seconds. So in exercise 5, it's a laboratory experiment this time on a trolley. It's moving in a straight line and the following values of velocity and time were recorded. So time, seconds, so 0 seconds, velocity was 0, so it started from rest obviously, then 1 second, the velocity was 5 millimeters per second, 2 seconds is 10, 3 is 15, so it goes on, okay. Looks like it's going to a constant velocity phase after 3 seconds, because at 4 seconds and 5 seconds the velocity remains the same. So I think that gives you an indication of what the diagram will look like. So you've got to plot the velocity time diagram again, given the information in the graph, and then find the acceleration of the trolley from the information given, the distance moved by the trolley in the first 5 seconds, that's the total distance travelled. And then it wants you to find the average velocity. That's an interesting one. We haven't come across that before. The average velocity is essentially the total distance travelled divided by the total time taken. I'll just write that down. So average velocity, sometimes it's called mean velocity. If you go back to statistical work, the mean velocity, the average velocity, it's just literally the total distance travelled divided by the total time taken. So that's what part 3 of the question wants you to find the average velocity. Just for your reference, if you sketch the information in the above table, this is the velocity time diagram you draw. I've shown the vertical axis here in terms of millimeters per second. It's really preferable to work in meters per second. And if you do work in meters per second, then the 5 millimeters per second squared would actually be 0.005 meters per second squared. But the area under the graph shown there would be the total distance travelled. And if you calculate the average velocity, it will be a value along here of 10.5 millimeters per second. I'd encourage you to attempt this question. So here are some tutorial questions for you to undertake. The answers to each of the questions are shown in the brackets on the right hand side. Here are questions 1A through to 4A. Question 5A and 6A. Again, all the answers are shown in the brackets. I'd encourage you to attempt these questions. I will show the solution to some of the questions on the following slide. Here are the solutions to some of the questions. Solution to question 1A, find the distance travelled. Solution to question 2A, finding the acceleration and also the distance travelled. Question 3A, calculating the final velocity in kilometers an hour. Solution to question 4A, calculating here the acceleration and also the distance travelled. And we've drawn a velocity time diagram and also in this case an acceleration time diagram. Notice the acceleration is constant. We assume constant acceleration in all these questions. And finally some further questions. Question 7A, question 8A, question 9A, and question 10A through to question 13A. Again, all the answers are shown in the brackets on the right hand side. I'd encourage you to attempt as many questions as you can. The more questions you undertake, the more developed your understanding of linear motion will become.